Okay, we're getting closer and closer to the end, boys and girls. This is assignment 6K. This is going to be called U substitution. And so the next two assignments are dealing with the exact same thing. Looking at the test, it's used on almost every question, U substitution or something close to it. Okay, what U substitution is built for is it's built for problems. Okay, so thinking about this. When I'm thinking of derivatives, okay, there's a bunch of different things that I can use. Like when I had a multiplication, well, what I get to use is I get to use the product rule. And that allows me to use derivatives using the product rule. Or if I had a division of complicated stuff, well, I have the quotient rule to use. And then what else did I have? Well, if I had, like sine 2x, things like that, then that implies that I have to use the chain rule as well. Now, all of these are applicable and obviously need to be done when you're talking about the world of derivatives. However, unfortunately, at this level, we do not have any of these things that we can use when using integration. Wah, wah. We can't use the product rule. We can't use the quotient rule. There's things that just don't make things very difficult. Like, so for instance, if I were going to be doing this top problem right here, unless I know like some crazy math, this is not possible to integrate right now. You can't do that. Or besides turning this into an incredibly large and weird polynomial, this is very difficult too with all the things involved. Okay, so something's got to give, especially when you're talking about these things where, like, you're talking about, like, when I see some of these things occurring, but how do I integrate with those concepts? And one thing that they allow us to do is this thing called U substitution. U substitution. So let's take a look at what the book says about it, and then I'll try to dumb it down to like our kind of level. So this is what U substitution is. All right. And so in essence, what you're going to see is this. If I have a function with an embedded function g, and I also know that the derivative exists somewhere else in the problem. All right, so what? All right, so say I have this embedded function g. Okay, and then the derivative of that g also exists in that same problem. Or some version of it, something really crazy close. So what I'm saying is this: if I have an x to the third, an x squared has to exist. I don't really care if the coefficient is the same, so it doesn't have to be the same, but as far as the x's and things like that are concerned, the x's have to exist as the derivative is being there. Okay? And so what's going to happen is we are going to take this as u, and we're going to make our problem simpler because we're going to eliminate this, and this ultimately is going to be u to the fourth. And so I'm able to integrate u to the fourth. Okay, here's how the process works. All right, so when I look at this, I see what's the most complicated part of this problem, and that's that portion of the problem. And also a good indicator of what is u is when you have like an x to the third and x squared, this is most likely the u. Because I'm going to be taking a derivative, so the derivative has to exist. So what I notice here is u is going to be 2x to the third minus 1. All right, Now, what we have to do is we have to take the derivative of u. So technically it's du dx, and that's going to be 6x squared. Again, don't worry about the coefficient. And so that is, in essence, dx. I multiply across dx. Okay. And for some of the problems, we have to get way more complicated than this. But right now, we're just learning the process. All right. Now, does the derivative of this u exist in the problem? Yes, it does. The derivative does exist in the problem. Awesome. Okay. However, we need this to match up with the coefficient that is currently there. Current coefficient is 1. So what would I do to my derivative to turn it into 1? I would have to multiply by a 1/6. And that's totally fine. And that's kind of part of the game. Okay. Putting this all together, what we get to do, if you're able to do this, is I can explain it one different way, but this is the simplest way. Okay, because. So this is going to be the integral. If you had to do anything, you attach that portion of the problem. The derivative exists, so this is going to be u to the 4th du. Okay, I would be a bad math teacher if I just left you like this. This is technically, mathematically what exists. I didn't lie up until that point, right? I didn't lie. Everything is there. If I solved for dx in this case, dx is equal to 1/6 and x squared on bottom. Okay, physically putting this substitution in. This is the x squared. This I just called the letter u. Oh, sorry, du is over here. And dx is now 1/6, 1/x squared du. That's what dx is. And so what occurs is this x squared cancels this x squared, and the 1/6 is hanging around. So this ultimately is 1/6 integral of u to the 4th du. I'm just so used to like my little tricks of how I quickly get my result. This is technically what is taking place. How I do it is I write it like this. I know that the derivative exists. However, I need that coefficient to be 1, so that implies that I would have a 1/6. I chuck that on, the derivative goes away, and I'm left with a u to the 4th. So I integrate this. This is u to the 5th, 1/5. There's a 1/6 already there. Okay. Plus c. It's not a definite integral, we still have plus c. And then when all said and done, this is 1/30th. U is 2x to the 3rd plus 1 plus c. There you go. That's your integral. Okay, let's get to some of these problems. Let's take a look here. Okay, what's the most complicated part? That's the most complicated part. And also notice that x squared is going to turn into an x, so the derivative does exist. Cool, cool, cool. So the most complicated part is 25 minus x squared. Okay, that means the derivative of u is equal to 25 goes away, minus 2x dx. Okay, so again, very technically, what dx is equal to is -1/2 and 1/x. That's technically du. Du over there. So I divide by -2 and I divide by x. So technically, what this would be is integral of the square root of u, -2x And then the dx, physically this dx is replaced with negative 1/2, 1 over x, and du. So let's see what things eliminate. So negative 1/2 eliminates negative 2, 1 over x eliminates x. And so I'm left with this integral of square root of u du, which is a problem that I can absolutely handle. Again, how do I do this? Again, because I've done this, I see that the coefficient needs to be negative 2, so what do I need to do to it? Nothing. It's all good. I don't have to add any extra pieces to this problem. So this is going to be equal to the integral of the square root of u, aka u to the 1/2, du. I didn't have to add any extra pieces. So I know that this derivative is going to go away, and then I just operate with the u. Sometimes I have to add extra pieces, which always go up front, in front of this integral. Again, this is a process. Again, it's tough. All right, so u to the 3 over 2, 2/3. And thus, this is 2/3, u being 25 minus x squared to the 3 over 2. Plus. I think this is the problem that I don't know if I use this one. Okay. So I see that the difficult part of the problem is x to the 4th plus 3. So the derivative of that is 4x to the 3rd dx. Does the x to the 3rd exist? Yes, it does. However, I want that to be 1. So I need to multiply by 1/4 to make that happen. Okay, so when that occurs, again, the derivative goes away. That's currently in the problem. The derivative goes away. And this is going to be 1/4 the integral of u squared du. Okay. U squared is u to the 3rd, 1/3. There's already 1/4 out there, plus c. So this ultimately is going to be 1/12, u being x to the 4th plus 3 to the 3rd plus c. Right, u is going to be 2x to the 3rd minus 1. So the derivative is 6x squared dx. I do have the x squared there, but I don't have the 6. I want that to be a 1, so this is 1/6. So I know that the derivative in the original problem is going to go away, and this is now the letter u. So I add all the extra pieces up front, and this is going to be the integral of u to the 4th du. Go ahead and integrate that. That is going to be u to the 5th, 1/5. It joins forces with the 1/6 that is already out there, plus c. So this is 1/30th, u being 2x to the 3rd minus 1 to the 5th power plus c. Again, if this takes you a while to kind of get your, like, I know it took me a long while. When I first learned this, holy cow, it was a slow process. It was a slow process. All right, so the difficult part of this is t squared plus 2. The derivative is 2t. I do have a t, but I don't have the 2, so I want that to be the number 1, so I want that to be 1/2. In essence, you divide down. So just So if you want it to be 1, it's 1 half. Okay, so that makes this integral 1/2 integral of u to the 1/2 du. Okay, u to the 1/2 is to the 3/2. That means 2/3. It joins forces with the 1/2. 2 simplifies, so this is 1/3. U is t squared plus 2. 3/2 plus. So again, they're going to get trickier and trickier. They're going to look more and more complicated. However, it's not really that complicated. Hardest part of this problem is this denominator. And so I'm going to make, and I also see an x squared and an x. So the u is probably involving the x squared. So that's 1 minus x squared. That's the u. Du is negative 2x. Okay, does x exist? Yes. So this is going to be negative 1/2 to undo that 2. So this is negative 1/2. And again, the derivative gets eliminated. This is the letter u, so this is in essence u to the negative 3. That's absolutely integrable. So this is u negative 2, so multiply by negative 1/2. Negative 1/2 is already up there. So this is going to be a positive 1/4 of u, 1 minus x squared, on bottom of a 2. So this would probably look like this. O plus c. Good gravy. Lost points on that AP test. Good grish. C isn't in the denominator, it's just plus c. So here we go, hardest part. I keep forgetting to put dx. You have to put the dx on that derivative. All right, so again, if there's embedded functions, and that includes insides of signs and things like that. All right, so here, the embedded function is pi x. Notice how the derivative of that exists. It's just pi. All right, I have the derivative there, or something like it. And so I get to eliminate that, and I get to use substitute right there. So it doesn't have to be a crazy complicated polynomial or something like that. Like almost anything, anytime that there's something inside of a sine or cosine, you probably want to be using this chain rule, or this use substitution. Okay, so I have that to be pi, and so that means that's all good. So that gets eliminated, so this is just going to be the integral of sine u. Sine goes to negative cosine. And then u is the same thing as pi x. Aha. Okay. Okay, so that's close, but that is supposed to be 1. Take a look at it. Because usually, like what my brain was saying, it's like, oh, that's going to turn into that, but that's going the wrong way. This is the thing that's getting chain ruled. So what derivative exists? And this is the derivative of that. Because they're denominators. Like my brain was trying to, like, playing tricks on me a little bit. All right, so this requires a -1, but other than that, we're in business. -1, so it's negative UV1. Okay, a bunch of different ways that you can get this. Notice that sine turns into cosine or cosine turns into sine either way. As far as derivatives are concerned, I know sine turns into cosine, so I'll just do it that way. So I'll say u is the complete sine 2x. So the derivative of that, again, don't forget the chain rule. All right, so that pretty much exists, so that will eliminate that portion of the problem. However, there's an extra 2, so I need to undo that. So this is a u, and then I need an additional 1/2. So u is sine, so this is going to be u squared. And so this is 1/4 u squared, and u is sine squared, excuse me, sine 2x, so this is going to be sine squared 2x. Again, the chain rule portion of this problem, the thing that is that up there. So u is going to be that 7x that was up top. Because ultimately, this is going to create an e to the u, which I can absolutely handle. And 7 does exist. Okay, again, you can separate numerators. So this is 5 e to the negative 2x minus e to the x, and so what I'm looking at is e to the x over e to the 2x. That's the same thing as saying e to the x squared. So what you can do is eliminate that square, leaving an e to the x on bottom of that second piece. And so that is e to the negative x. All right. So here we go. This first one. Okay, I'm not pay no number mind to the 5. If you want to put the 5 in here, that's fine. It'll come out in the wash. So to eliminate the negative 2 that's created, I have to have a negative 1/2. Okay, there's a 5 already out there. Again, don't worry about that. So this is going to be, this part of the problem is going to be 5 negative 1/2 integral e to the u du. That's that one. I'll call that u1 or something like that. On this right-hand portion, u is negative x. So du is equal to negative 1. And again, I wanted that to be 1, so that requires a negative 1. I know it's a minus, but you get the idea. So this is going to be minus, and then there's a negative 1 integral e to the u. I'll keep going with the blue, so this is going to be plus integral of e to the u is e to the u, a different type of u, and then plus c. Again, that's red u. So negative 5 over 2 e to this u is negative 2x plus e to the other u is negative x plus c. Get all of it. Let's shrink everything down. Shrinky dinks. All right, so this is holding the whole process up right there. Chain rule. So all of that exists except for that. Oops, sorry. I need that to be 1. So that implies it's not equal to, it implies. So that gets rid of the derivative that exists, things like that. So this, all this requires is a 1 over pi. All it costs you. Again, when they have trig, usually the inside thing is the u. Okay, definite integrals. So all of these have been indefinite integrals. So definite integrals you can do a couple different ways, okay, with u substitution. So this integral of number 71 is requiring a u substitution. How do I handle it when it's a definite integral? Okay, so you can do it 2 different ways, and I strongly recommend one of the ways, but I'll show you the bad way first. I'll show you the bad way. And so here's the bad way of doing it. So I create this u substitution. And so this creates a 1/2 integral. Now this -1 and 1 are still considered to be x's. All right, and this is why this is the bad way, and I'll show you. So that x gets eliminated, so this is going to be u to the 3rd du. So I integrate, so this is u4, 1/4. You don't get a plus c, because this is being evaluated at -1 and 1. Okay, so grab it all. Let's take it all. Okay, so this is 1/8, and then the u is actually x squared plus 1 to the 4th. And now we're back in the world of x's, so this is back to negative 1 and 1. And then you can go ahead and plug and chug into that. So 1 in for x would be x squared plus 1 to the 4th. So that would be 1/8. This is 16 minus negative 1 going in. Again, that's x squared plus 1 to the 4th. 16. That's equal to 0. Okay. This is a bad method. I don't like this method. I mean, it works. That is the answer, et cetera, but it's a poor method. Okay, here is my method. Well, not my method. I didn't invent this. But here is the method that I prefer, and you have to do a little teeny tiny additional thing up front, but it'll make your world a lot easier. Here's what you do. You'd start your u substitution just like you normally would. So u is going to be equal to x squared plus 1. You take that derivative, 2x, yes, that exists. However, without the 2, so that's a 1/2. So we're through the process 1, so that divides, so that's 1/2. All right, now, before going and rewriting everything right now, what you want to do is you want to reevaluate the upper limit and the lower limit. You want to reevaluate the upper limit and lower limit. How you reevaluate it is you plug it into the u. You plug it into the u being x squared plus 1. So 1 is going to be 2. Negative 1 is going to be 2. All right? So I reevaluate the lower and upper limits. Okay. This saves you a lot of writing and a lot of turmoil right there by taking that one little additional step about reevaluating the upper and lower limit. So what this would become is this. I rewrite this. So this required a 1/2 integral of u to the 3rd. Now I put in my new limits. So the upper limit is now 2, the lower limit is now 2. So I know this answer is going to be 0, but I'll just show it. So reevaluating the limits, okay, this is going to be u to the 4th, 1/4, 1/2. And now that I reevaluated the limits, I don't have to turn this back into an x. I don't have to turn this back into an x. I just use the u as u to the 4th. So 2 to the 4th minus 2 to the 4th. So I don't have to turn it back into the x at that point. That's the method that I prefer when you have to evaluate a definite integral using u substitution. All you do is reevaluate the lower and upper limits, and then you do not turn this back into an x. You do not turn that back into an x. You just go ahead and plug into that u. Okay, find the area bounded. So we have an e to the x. Y is 0. X is 0. X is 5. So this would be the integral from 0 to 5 of e to the x. Everything to the 0th power is equal to 1. Don't forget that. Okay, use substitution on this guy right here. Okay, so again, that eliminates the derivative. This is now the letter u. All it requires is a negative 1/6. Average value, easy peasy. Okay, let's set up the rectangle. So the rectangle is on the interval of 0 to pi over 4, so that's pi over 4 minus 0 of the average value. And that's going to be equal to the curve from 0 to pi over 4 of that mess gross. Okay. This is most likely going to be my u here. Yeah, because tangent creates a secant squared. So the derivative does create it. So it's all good. I'll change colors here. Okay, so u is going to be 1 plus 2 tangent x. du is going to be 2 secant squared x, which is close. I don't want 2. Okay, but because it's a definite integral, I'm going to reevaluate the pi over 4 and the 0. Pi over 4 is square root 2 is 2, so that's 1. So this is going to be 3. 0 has a sine of 0 and a cosine of 1, so that's going to be 0. So that's going to be 1. Again, tangent is sine over cosine. All right, so what is created here? So I'm going to divide by this pi over 4, so that'd be 4 over pi with the division. And so that's coming from the left-hand side. The u substitution itself is creating a 1/2. The integral is reevaluated from 1 to 3. All of that crap is now u to the 3rd du. This is going to create a 1/4, u to the 4th, from 1 to 3. So this is what, 2 pi over 1, And this is 3 to the 4th. That's what, 9 and 9, 81. 81 minus 1. I feel like I did something wrong here. Oh, no. Aha. So this is going to be 80 over 2 pi, which is what, 40 over pi. Haha! No. There it is. Okay, again, a rate. So a change in position, a net change in position is an integral of its rate. Okay, change in position is an integral of its rate. So they give you a rate, how many gallons, so what's the change in position from 0 to 12? So the net change in the amount of liquid or whatever is an integral from 0 to 12 of this. All right, so here we go. U substitution. U is equal to negative 0.12 T. The U would be negative 0.12 dt. I want that to be 1600. So 1600 divided by negative 0.12 is that. I'm going to store that as the A or something like that. Oh. Maybe I won't do that. What I'll do is I'll just say, hey, I want this to be the number 1. And so 1 divided by negative 0.12 is going to be something that I can get my hands on, negative 25/3. And so what I'm doing is I'm taking out the 1600, and I'll worry about that at a later time. Okay, so right now where I'm at with this is I have a 1600 on the outside. I have a negative 25/3 on the outside. I have the e to the u du, but all I need to do is now reevaluate the 0 and the 12 to get what I need. So the 0 and the 12. So the 12, again, these are going into u. So 12 times negative 0.12 is negative 1.44. 0 going into u is 0. Okay, e to the u is e to the u. And then again, as I said, I'll worry about this. 1600 times negative 25. This is why you couldn't really understand what I was trying to say. E to the u is going to be e to the negative 1.44. I'll just go ahead and put all of this in now. Minus e to the 0, which is 1. And then I'm going to be multiplying by negative 40,000 divided by 3. Done.